Okay, so this is going to be the first lecture on mathematical analysis, and we are going to essentially study real analysis. This is going to be the first lecture on real analysis. Okay, and today we are going to basically discuss what the real number system is. Okay, so straight away we start with the lecture. Now, the question is that from where do we actually construct the idea of real numbers? Okay. See, historically, the most important number system was the natural numbers. Okay, was the natural numbers. Okay, numbers were actually a measure of count. Okay, I hope we people already know about barter systems and profits, selling things and all. So, what is the main idea behind selling something, behind profits? We actually count how much we buy, how much we sell, okay, how much more we sell, how much less we buy, and so on and so forth. And we know the counting of things in real life is actually what we do using natural numbers. We buy two cows, we buy 3 grams of rice, and so on. So the existence of natural number is mainly due to its practical use in real life. Okay. Now, as mathematics progressed, we start counting backwards and we produce what we call the negative natural numbers. And together with that, we form a complete set of what we call integers, right? So, what is the natural number system basically? It is the set of all the numbers 1, 2, 3, and so on. I'm just giving you a practical idea, okay? I'm not giving you a mathematical idea of how natural numbers were constructed, what piano axioms and all. Okay, to understand the proper construction of natural numbers, we need to understand what are piano axioms. In my channel, there is already a brief lecture on piano axioms. You can see that. But here we are actually trying to, just practically understand the essence of numbers. Okay. Yeah. So this is natural numbers, and then what we do actually, we go backwards and we produce what are negative natural numbers. So if this is the set of natural numbers, then we already have the set of the negative natural numbers, which is -1, -2, -3, and all. Okay. Now we add the number 0 to this set. Okay. 0 is the measure of nullity, the measure of voidness or emptiness, whatever you say. And then we form a system of numbers which we call the integers. Okay. So integer is basically the set of numbers. We can say minus n such that, sorry, is the set of the numbers, the form 0, 1, 2, and so on, and here you have -1, -2, and so on. Okay, a never ending set. Clear? Got it? Okay. This is the actually the set of integers. Okay, the set of integers. Okay. Now from the set of integers we try to construct one more set which we call the set of rationals. So what we actually do is that we try to fill in the gaps between two numbers. Okay, we try to fill in the gaps between two numbers. See, there is no number between 1 and 2. Okay, between 1 and 2 there is no integer. There is no integer. But we know that the number 3 by 2, this is greater than 1 and this is less than 2. Clear? Clear? So what we try to do is that we try to form a set which obviously includes all the integers as well as it includes the gaps between two integers, and we name that particular set as the rationals. as the rationals, and rationals basically contain the set of all the numbers of the form p over q such that p and q belong to the set of integers and q is non-zero and 0. Clear? Got it? We can also add one more point to it, that the GCD of P and Q is 1, so that we neglect the repetition of numbers. What we actually try to say is that suppose you have the number 2 over 4. Okay? You have the number 2 over 4. Now this number 2 over 4, this can be taken as 1 over 2 because we can cancel 2 from both the numerator as well as the denominator. Okay? So we form this number and we maintain uniqueness in it. Okay? Uniqueness in the sense that we take into consideration only one particular representation of each number. Okay? If you omit this particular condition, that the numbers p and q are co-prime, then you will include all the possible representations of every number. That is also for now it's okay. It's okay to consider that as well, so that we can visualize a broader field of numbers. Okay. Okay. Now what happens is that after construction of rationals, we still find that there are gaps in rational numbers. Okay. For example, there does not exist any rational number such that its square is the number 2. Okay. Now first we try to prove it as just a motivation for the lecture. So proof. What we do is that suppose there exists a y in rational number y such that y square is 2. Okay. Now let y2 be of the form p over q such that GCD of p and q is 1, both are obviously integers, and q is non-zero. Okay. Now if so, then that implies that p square over q square is 2 as well, which implies p square is equals to 2 times q square. Now if you have basic idea of number system, you know that this implies that p square is an even number. Rather we write it as 2 divides p square. That is, p square is an even number. Now this is a very pretty simple proof, or pretty simple fact, that if 2 divides p square, then 2 will also divide p. You can try this as an exercise. It is very simple. Okay, you can also then 2 also divides p. Okay, that is, if p square is even, then p is also even. So that implies we can write p as some 2 into k, where k is also an integer. Right? Pretty basic facts from divisibility. Got it? Okay. Now if so, then putting 2k in place of p square, we get 4k square is equals to 2q square, which implies 2k square is equals to q square. This again says that 2 divides q square, which implies 2 divides q. Now suppose we mark this equation as 1, sorry, this statement as 1 and this statement as 2, then 1 and 2 implies that GCD of p and q cannot be 1 because we have a common factor, that is 2. Right? So this is a contradiction to our assumption that GCD of p and q was 1, which implies that there cannot exist any rational y such that y square is 2. Is it clear? Now, what is the process we actually follow to prove this statement is what we call the proof by contradiction. as the lecture will go on, you will be more comfortable with such proofs. I'm just giving you a basic idea what is proof by contradiction. What is proof by contradiction? So suppose we are to prove this statement Pn. Okay, we are to prove Pn. To prove Pn, we actually consider the negation of Pn. Okay, we consider that negation of Pn is true, and we reach a point which contradicts contradicts the assumption of negation of Pn to be true. Okay, like what happened here is that we are to prove that there exists no rational number such that its square is 2. We assume that this happens. There exists rational number such that y square is 2, and proceeding we reach a point where we see that our assumption of the truthness of the statement we considered is contradicting, right? That implies that the assumption cannot be true. So Pn must be true. Got it? This is what we call proof by contradiction. Okay. So what we conclude from here is actually that there are still certain holes in rationals which are to be fulfilled so that we get a complete number system with all possible properties of numbers and all possible properties of mathematics, right? To fill such holes, we actually form a larger field of number system which we call the real number system, which includes all rationals, all integers, all naturals, as well as the holes inside the rationals. And these holes inside the rationals are what we actually call the irrational numbers. Okay, so the holes inside rationals are termed as irrationals, and rationals plus the irrationals make up the complete number system which we call as the real number system. Okay, as the real number system. Clear? Clear? Got it? So it is pretty clear, right? It is pretty clear. Okay. Now, actually, now we actually study the properties of real number system, which actually makes it a bit unique in the case of numbers. Okay, there are certain properties which only real number system bears and no other system bears. Okay. Okay. Now see. Now see. Okay. Yeah. So now we start with what we call ordered sets. Okay. What we call ordered sets. Now, before understanding ordered set, we first understand what actually is an order. Okay. So we consider that let S be a set. See, I'm assuming that you people know the basics of set theory. Okay. You people must know the basics of set theory. Okay, you have studied in your schools as well. Clear? So let S be a set. An order on S is a relation denoted by this symbol with the following properties. With the following properties. Okay, this is only this symbol. Yeah, the following properties. Number one, if x belongs to S and y belongs to S, then either x is less than y, we pronounce it as is less than. Okay, so x is less than y, or x is equal to y, or y is less than x. Okay, this is more conventionally written as x is greater than y. Clear? Clear? Is true, rather is true. Okay. Got it? Okay. Number two is that if x, y, and z are in S, then x less than y and y less than z implies that x is less than z. Clear? Clear? So these two properties are obeyed, and then we say that the relation is actually called an order. Okay, these sorts of relations are called orders. Clear? So an ordered set is basically a set on which an order can be defined. Okay, so if for S such an order exists, then S along with the order is called an ordered set. Is called an ordered set. Clear? Clear? Now we move on to certain important definitions, which will be of use later. Definition. That suppose S is an ordered set, and we take a subset of it. Okay. Now, if there exists some beta in S such that small s is less than equal to beta, less than equal to is basically less than or equal to this relation. Clear? Clear? Okay. Equal to in very practical sense means that the both the numbers are same, both the numbers are identical in the set, nothing else. Okay, so such that s is equals to beta for all less than equals to beta for all s in E. Okay, then we say that the set E is bounded above and beta is an upper bound of. In similar way, we can say that if there exists some alpha in S such that alpha is less than equals to S for all S in E, then E is bounded below and alpha is a lower bound of. Clear? Two very similar statements. That's the order being defined in a different way. Is it clear? Is it clear? Okay. Now see. Now, in this case, suppose you have an ordered set S and you have a bounded set E. Okay. Suppose E is bounded above. We say a set is bounded, simply bounded, if it is both bounded above as well as bounded below. So we actually carry out a definition using the concept of bounded above, and the similar concept will also get applied for bounded below. Okay, so suppose S is an ordered set and E contained in S is a set bounded above. Okay, suppose there exists some, suppose some u in S such that, point number one, S is less than equal to u for all small s in capital S, that is u is an upper bound of S. And number two, if S is less than equals to some beta in S for all small s in S, then u is less than equals to beta. Then we say that this number u is the supremum, or the least upper bound of E. Okay, is the least upper bound of E. One more definition of it is that the second point, let us add a third point to it, that if there exists some gamma which is less than alpha, less than u, sorry, which is less than u, then gamma is not an upper bound. Gamma is not an upper bound. Okay. So if both these properties, or this third property also, suppose if these three properties are considered and are true, then this number u is said to be the supremum or the least upper bound of E. Clear? We use this notation that u is the supremum of E or LUB of E. A similar definition also gets applied for what we call the greatest lower bound or the infimum of E. That is, we apply L is the infimum of E or the greatest lower bound of E when, if L is a lower bound of E and if say alpha is a lower bound of E, then L is greater than equal to alpha. Clear? That is, in very similar sense, least upper bound is basically the smallest of the upper bounds, and greatest lower bound is the greatest of the lower bounds, in very simple sense. Is it clear? Is it clear? Now suppose we take this set, say example. Okay, suppose we take this set. E is the set of all numbers of the form 1 over n such that n belongs to natural numbers. So E is basically the numbers 1, 1 over 2, 1 over 3, 1 over 4 and so on. Okay. Now what is the upper bound of E? So let us say what is the supremum of E instead, because that is the terminology we are going to use mostly. So what is the supremum of E? So it is very evident the supremum of E is 1. Okay, the supremum of E is 1 in this case. Clear? What is the what is the infimum of E? Now practically notice this, that as n grows in size, 1 over n approaches to 0. You cannot have a number of the form 1 over n where n is in the natural numbers to be less than 0. You cannot have negative numbers inside this set. The least number you can reach approximately is 0. So 0 is indeed smallest of all these numbers. So the infimum of E is 0. And any number you take less than 0, they will also be smaller than all the numbers in the set. Therefore 0 must be the infimum of E. Now what major conclusion we draw from here is that, see, supremum of E is inside E, but the infimum is not inside E, because you cannot appropriately reach exact zero. Okay, you can just get very close to zero inside this set, because you cannot practically hold on to infinity. Okay, if you practically hold on to infinity, that is, suppose infinity is indeed an extremely large number whose reciprocal gives you 0. That is the only possible case for this set to have the element 0. If that was possible, then only 0 would be an element of the set. But actually 0 is not an element of the set, but you get extremely close to 0. Clear? But exactly you cannot reach 0 inside the set. So the infimum of E is not inside E. So what we actually try to say in this case is that a set which is bounded above or bounded below or is simply bounded, it has its supremum in it adds its infimum, but that supremum and infimum, it must not, there is no condition, there is no restriction for the supremum and infimum to be inside that very set. Clear? Clear? They may not be inside the set, but they exist outside the set, like in this case. Okay, if you consider E to be a subset of rationals, let's say, if you consider E to be a subset of if you consider E to be a subset of rationals, then obviously the infimum is in the rational numbers. Okay, clear? So it's not mandatory for the supremum and infimum of certain set to be inside that set. It can be outside that set. Is it clear? Is it clear? Suppose we consider the set. Suppose we consider the set 1, 2, 3, and so on. That is basically the natural numbers. Then it obviously has an infimum which is 1, which is obviously inside E. But is it bounded above? It is not bounded above, right? Because in a pretty simple sense, if you fix some n in n, then n plus 1 is greater than n, obviously. So whatever number you take from the set of naturals, you will always get a number greater than that. So it will not be bounded above. So it has no upper bound. It has no least upper bound as well. Clear? In similar sense, you can also create a number which is not bounded below but bounded above. Got it? Clear? Okay. Now we have this definition. The definition of the least upper bound property. Okay. Say this. Suppose S is an ordered set. Suppose S is an ordered set. E is contained in S, and E is bounded above. E is bounded above. Then S is said to have the least upper bound property if the supremum of E exists in S. Clear? The supremum of E exists in S. What we actually mean to say here is that every bounded set in some ordered set has a least upper bound which is always there in the bigger set which we are talking about. Okay, for say in case of real numbers, suppose this set which we are talking about, let's say here this set which we are talking about. Okay, this is a very specific thing. I'm just using this specific case to make you understand what actually we mean by the least upper bound property. That is, you take an ordered set Q and you take this set which has an upper bound 1 is inside Q, least upper bound 1 which is inside Q, and it is also bounded below by 0. Its greatest lower bound is 0, which is also inside Q. Okay. Okay. I'm not telling that Q has the least upper bound property, but I'm just making you understand what do we actually mean by it. Every bounded above set has the least upper bound inside the bigger set to which E belongs. Clear? Clear? Okay. Now, see these the least upper bound and the greatest lower bound, they possess very important properties which are actually of high use. Okay, so we need to understand those one by one. We are going to move into greater details regarding these, and we are going to understand this for because these are the most important concepts which we need to learn to study further in real analysis. Okay, now we first move on to a very important example, an elaborate example to understand this thing. Suppose we are talking about Q, the set of rationals. Okay, we choose a set A in Q such that A contains all those rationals whose square is less than 2. Okay, and we take the set B of all the rationals Q, such that its square is greater than 2. Clear? Clear? Okay. Now see. Now what we actually try to do here is that we need to show, or we will show rather, that A contains no largest number and B contains no smallest number. Okay, so our goal is to prove that A contains no largest number and B contains no smallest number. Okay. Okay. Clear? Now how to do this? See, we can use this concept inside here that whatever p we take from A, whatever small p we take from A, we can always find another rational, say p dash, such that p dash is greater than p. Therefore, we have no largest number in A. And same thing we do in B, that whatever number we fix q in B, we can always find a number q dash such that it is less than B. Okay, let us say this. Okay, so in A, let p dash be the number p minus p square minus 2 by p plus 2, which is actually the number 2p plus 2 by p plus 2. Okay, then we can see that p square minus 2 is the number 2 times p square minus 2 by p plus 2 whole square. We're just squaring and subtracting 2 from both the sides. It is very simple to see. Okay, now so this is p dash square. Okay, now if p is in A, then p square minus 2 is less than 0. If p square minus 2 is less than 0, then what does that mean? If p square minus 2 is less than 0 in this here, then what do we get? So this is very simple here. P dash square will be then greater than P. Sorry, P dash will be greater than P. Right? P dash will be greater than P. Got it? Got it? This we can conclude from here. Okay? This we can conclude from here. And P dash square minus 2 is also less than 0. This we can conclude from here, which will obviously imply that P dash is also in A. Okay, so here is the proof for the set A. A similar proof will also prove the required proposition in B. Okay. Okay. Now we can do it from here only. See, we consider the same things. Okay. What we actually do is that in that case is P square minus 2 is greater than 0. So that will imply that P dash will be greater than 0 and less than P. Okay. Let me just do this here, that we consider P to be greater than 0. Okay. Okay. In A and B, let's say P is greater than 0, and then we do these things. Okay. And P dash square minus 2 will also be greater than 0 by the second statement, which will imply that P dash is inside B. Okay. Okay. So this actually shows that we never actually reach the number root 2. We never actually reach the number root 2 in either of the sets. But if you carefully notice the two sets and idealize the concepts of supremum and infimum, you will notice that the infimum of B and the supremum of A will be the number root 2. The number root 2 is basically, see, if we take P square as 2, then P is taken to be the number root 2. We have that the infimum of B and the supremum of A is the number root 2. But root 2 is nowhere in Q. Okay? Root 2 is nowhere in Q. Because we have already started our discussion considering that there exists no rational number whose square is 2. That means that Q does not have the least upper bound property. Is it clear? Is it clear? Q does not have the least upper bound property. I'm giving you a brief exercise. Prove that the symbol which carries its usual meaning in number line is an order for Q. Okay, prove this. Clear? Okay. Now we have a theorem here to discuss, which will be the last theorem of today's lecture. In the next lecture, we will be starting with our concept of fields, and then we will be understanding the essence of the real numbers. So the theorem says that suppose S is an ordered set. Suppose S is an ordered set with the least upper bound property. B is contained in S, B is non-empty, and B is bounded below. B is bounded below. let L be the set of all lower bounds of B. Then prove that, or then alpha is the supremum of L, exists in S, and this alpha is actually the infimum of B. So let me make the theorem a bit clear. So we take an ordered set which has the least upper bound property. Then we take a set which is bounded below. Okay. And we show that the supremum of the set of all lower bounds of the set B is indeed the greatest lower bound of the set B. Okay, I'm just giving you an example. We are taking that particular example only. Say we take the say I'm giving you this fact here that real numbers are ordered. Real numbers have the least upper bound property. We will prove it later. Have the least upper bound property. Okay. This is the property which makes it different from the other important sets like the rationals, integers, and all. Okay. Okay. So inside R, suppose we take the set S as, sorry, let me take S as R. We abide by the notations in the theorem, and we take B to be the set. Say say 1 by n. N belongs to natural numbers. Okay. This set is obviously bounded below by 0. Now see what is L in this case. So L is basically 0 and every number less than 0, right? So L is basically the set of all those elements L in R such that L is less than equal to 0. What is the supremum of L? 0. And this 0 is indeed the infimum of B as well. Is it clear? This is what we actually need to prove. So see. So now see. So since B is bounded below, that means there exists lower bounds of B, which implies L is non-empty. L is non-empty. Okay. Clear? Now see. Now let Y be in L. Then Y is less than equal to X for all X in B. This implies X is an upper bound of L for all X in B. That means every element of B is an upper bound to the set of all its lower bounds. Okay. So this means that L is bounded above. L is bounded above. Which implies that L has a supremum in S because S has the least upper bound property. So L has a supremum in S. Let alpha be the supremum of L. Let alpha be the supremum of L. To prove that this alpha is the infimum of B. Okay. Now see. If there exists some gamma which is less than alpha, then gamma will not be an upper bound of L. Then gamma is not an upper bound of L because alpha is the supremum of L. Okay. Then that will mean that gamma will not be in B because every element of B is an upper bound of L. Is it clear? Is it clear? Now what does that mean? Now, So so any element less than alpha is not in B, right? So that specifically means that alpha is indeed less than equal to every element in B. So alpha is less than equals to x for all x in B, which means alpha belongs to L. Clear? Now, if alpha is less than beta, then beta is not in L. Why? Because if alpha is less than beta, then beta is an then beta becomes the see. If alpha is less than beta, then beta is no more the lower bound of B, right? Because there will always exist some element in B which might be less than beta or might be equal to beta, considering the hypothesis which we are carrying out over in this proof. So that means beta will not be in L, since alpha is the supremum of L. Clear? Clear? So we have showed that if alpha is in L, beta is not in L if beta is greater than alpha. So what does that mean? That alpha is a lower bound of B, but beta is not if beta is greater than alpha. So that means alpha is the infimum. Okay, that is all with this. Clear? What we actually do is that we consider alpha to be the supremum of L after showing that L is bounded above, and then we show that any number which is greater than alpha is not an lower bound of B. That means alpha is the largest possible lower bound of B, and that means alpha is the supremum of infimum of B. Is it clear? So let this lecture be up till this much, guys. In the next lecture, we will be talking about fields, and then we will moving on to the concepts of real numbers. So meet you guys in the next lecture.